initialize Genesis sequence.
All right, welcome everybody. So I'm here to talk about Project Valhalla. I have talked about this before here at Devoxx, but we've made a lot of progress since then. I don't know who gave Valhalla this moniker, Java's Epic Refactor, but I love it. It's really an excellent description of what it is that we're doing, because Project Valhalla is a deep cut that's reimagining the relationship of the language with the underlying memory, in the computer. And so it's cutting through the language, the runtime, the libraries, and it's a significant effort. We've been working on this for at least 10 years now, and the good news is that all of that work is really bearing fruit. And so over the last 10 years, we've built multiple prototypes, we've done a lot of experiments, and we feel like things have converged and we have our answers. In particular, what we've been focusing on in the last 2 years is on the place where it meets the human. So we've been focusing previously on the place where it meets the machine and proving that it's possible to get the results that we're looking for. But we've turned our attention to how do we integrate this into the programming model and make this less intrusive, make it look less like it's been nailed on the side, and how do we enable people to move from the code they have today to the code that they want to have tomorrow. And one of the challenges of a project like this is there's a performance motivation to it, but we don't want it to be a performance feature. We don't want to have keywords in the language that talk about memory layout or flattening. That's a road to failure. Every language that's tried that has failed with it. And so the challenge is finding the right way to frame semantically what the programmer wants in a way that the VM can provide the desired optimizations. So as background, I'm going to talk about what the goals are, and then we're going to get into the details. So the JVM operates on two kinds of values, primitive values and object references. And if you read the JVM specification, it says absolutely nothing about how objects are laid out in memory. But if you get out your magnifying glass and read carefully between the lines, there's basically only one way to do it. The semantics of the language and the VM basically force us to lay out objects kind of the same way that we imagined that they were in computer science classes with box and pointers. So object references, they end up getting forced to be represented as pointers, and objects are forced to be represented as blocks of memory, absent heroic optimizations like escape analysis, which you can't, are nice when you get them, but you can't count on. So if I have a point, and I have a rectangle that has 2 points, and I say make a rectangle, I'm going to get a memory layout that looks like the thing that you remember from computer science class. So I have a pointer to a rectangle object that has a header, and then the rectangle object has 2 pointers in it, and each of those point to another object with a header, and those objects have my numeric payload in them. And there isn't anything wrong with this layout. It makes perfect sense. But for some applications, this may not be as performant as we'd like it to be. In particular, it's not very flat, which is to say that we have these little islands of data that are connected by pointers. And it's also not very dense, which is to say a lot of the memory that's used by that layout is used by objects, headers, and pointers, and not by data. And in the last 30 years, the relative cost of memory operations versus computational operations has diverged. So 30, 40 years ago, a memory fetch and an arithmetic operation were about the same cost. Memory operations have gotten more expensive, arithmetic operations have gotten faster, and as a result, the cost models have diverged. So if you have a non-flat memory layout, you're inviting cache misses. Cache misses are expensive. And so the question that Valhalla asks, or one of the questions it asked, is under what conditions would we enable the VM to lay out a rectangle like this instead? And sometimes this is what we want. The same thing is true, even worse, with arrays. If I have an array of point objects, every point is an object. To get to each point, I have to traverse a header. That's an indirection. That's possibly a cache miss. And so if I'm going to march down this array and read the x and y values and then go on to the next one, I'm likely to give up of all the benefits of things like cache locality and hardware prefetch. And a lot of the time, what we want is a layout that looks like this. Not all the time, but a lot of the time. And so the questions we ask are, how do we make this possible? What code are we asking people to write? And the sort of the big overarching question is it possible to do this without turning Java into something it doesn't want to be? So this is surprisingly connected to the problem of primitives, and Java has always had a rift between primitives and objects, and you can think of this as Java's original sin. The distinction between primitives and objects was a forced move back in 1995 because at the time, we didn't even have we didn't even have JIT compilers, and no one could have taken a language seriously if arithmetic was as slow as it would have been had we done it the beautifully object-oriented way, right? And so it was a forced move back then, but it's something that we've been paying for ever since. It's a pervasive source of friction, and you can see it probably in your own reaction when if you have to make an array list of integer, everybody feels a little dirty when they do that, right? And you're like, there's part of your brain saying, oh, there must be a better way to do this, right? And that's us getting in our own way because of this pervasive friction. The problem, and I alluded to this yesterday in my keynote, the problem with introducing a split somewhere is the next layer that builds on it is going to have to split again. And the layers that build on that are going to have to split again. And so when we did generics had to take on this big compromise where you can generify over all the types except these 8. Which are really useful types, And if we have an array list of int, it's not backed by an int array. It would be backed by an integer array. And the layout of that looks just like the layout of the array picture I showed you a minute ago. And then it got worse again in Java 8, where we had this explosion of hand-specialized functional interfaces and classes like instream and int-long function. Nobody wanted that, but that was the consequence of the compromise that we made in 1995. And so so the genesis of Project Valhalla was in recognizing this is what we ended up having to do, when we got that far up the stack and we didn't like it. So primitives and objects couldn't be more different. One's built in, one is user defined. One has members and supertypes, the other doesn't. One has identity, the other doesn't. One is nullable, the other isn't. One can be used without running a constructor. One can't be used until you run a constructor. One is polymorphic. One is imagine this 18-dimensional space describing language features. They're at diametrically opposite points of the cube. And that's a challenge for idiots like me who decide, oh, we should unify these concepts. But that's exactly what we've been doing in Project Valhalla. So in some sense, we don't need primitives. We can do everything we want with classes, but we use primitives for a reason. They're faster. The reason they're faster is they are denser and flatter than objects are. And this means that we're putting users in a situation I hate putting users in, which is you have the bad choice of I could write clean code and nice abstract object-oriented code, but then it might be slow, or maybe I'll think it's slow, and that's just as bad. Or I could do nasty, unmaintainable stuff with primitives. And which one do you think people choose? Right? And so when you're in a situation where people perennially choose wrong, you need to give them a better choice. Another challenge with primitives is we have 8 primitive types. It is really, really difficult to add a 9th primitive type, and it certainly doesn't scale to add 100 new primitive types. And are these 8 primitive types exactly the ones we want for the entire future of computing? Hell no, right? Where's my float 16? Where's my complex? Where's my fixed point classes? They have to be classes. They can't be primitives. And if you have read Guy Steele's 1998 paper, Growing a Language, or watched the video, he lays out a vision, for how we can achieve the benefits of built-in numeric types without them being built in. So in some sense, we've been working on Valhalla for 30 years. So that's a long-winded wind-up to get to the goals of the project. Flatter and denser memory layouts, unifying objects and primitives, healing the rift between objects and primitives, and enabling new numeric types to be added as libraries, not built-ins, while retaining the same runtime benefits that primitives have today. And ideally, this should give us the best of both worlds, right? So you have all the abstractive power of classes and all the beautiful runtime characteristics of primitives. And so the sort of war cry that, like, we got ourselves all worked up with in the beginning was codes like a class, works like an int, best of both worlds. And delivering that is an epic refactor, but the goal is to make it look like it was there all along so that people can say, what took you so long? 10 years we've been chipping away at this. Experiments, prototypes, explorations in the language, the compiler, the runtime, the JIT, the libraries. And all of that yielded to the steady, like, bashing your head against the problem that we've been applying to it, for the last 10 years. But the hardest part is where it meets the humans, was identifying a sensible programming model that is easy to understand, doesn't look bolted on, and that supports, most importantly, supports graceful and gradual migration from the code that we have today that could have been values, but weren't because we didn't have that feature in the language when they were written, to true value classes. And the light, you can see the light at the end of the tunnel. So I talked about this at the keynote. Probably almost all of you are at my keynote, so I won't go into the details of my peak of complexity model, but let's just say that about 2 or 3 years ago, we were at the peak of complexity in Project Valhalla. We had a solution that seemed to work, it ticked all the boxes, and if you tried to write code with it, it was horrible. And we didn't want to inflict that on you, and so we spent the last several years pruning back the complexity, pulling unnecessary features out, and amazingly, the complexity really has collapsed. And this collapse went on until about 6 months ago, where we kind of stared in amazement of like, oh my God, where did all the complexity go? We started out with a model that had new bytecodes, new verifier rules, new type descriptors in the VM, new constant pool forms, and if you read the JVM spec for JEP 401 now, none of that. It's a new bit on classes, a new bit on fields, a new attribute on fields, and that's it. It's like, where did it all go? It's amazing. So we're totally ready for the rear view second guessing of what took you idiots so long. Okay, so flatness and density, what are the impediments that we have today? So there's a number of them. The biggest one is object identity. Objects have identity, and this means in reality that objects have to live in one place, or at least one place at a time. The garbage collector can move them, but there is always an official copy of the object, and that is necessary if, for example, you want to have mutability, because there has to be an authoritative place to store the value. Another challenge it's a little bit like a Spanish Inquisition sketch. Amongst the impediments to flattening are identity, nullity, initialization. Object references are nullable. That means you need a bit pattern to represent null, in addition to all the other bit patterns to represent the state of your object. So if you have a class that's dense in its like long, you need 2 to the 64 2 to 64 values of long, so you need 64 bits. If you need another bit pattern, now you need 65 bits. That means you need 128 bits. So nullability is an impediment to, is a density problem, and it's also a flattening problem for surprising reasons. And in addition, like even if you have like heroic encodings for null, like using the low bits of pointers and things like that, you create this data dependency that says, I can't use these bits unless I know these bits are in this state, and like I have to teach the garbage collector that too, which is not pleasant. So nullity is an impediment. Initialization is a big impediment. So objects have to go through a constructor before they can come into being. Primitives, on the other hand, you can use them without initializing them. And int, comes all set up with the value 0, which is an excellent default value, and you don't have to run an int constructor to start using it. Not all classes that might want to be values have that characteristic. So like complex, okay, complex does have a good default value, 0, but local date doesn't. And so that means that if there's no good default value, you have to go through some kind of initialization. And the way initialization works with constructors today is leaky. That it's sometimes possible to expose fields in their default state before they've been assigned a value by a constructor. And if that default state is just an unfortunate default like 0 or null, well, that's unfortunate but not a disaster. But if that state is actually the an instance of a class that is not a valid instance of that class. It's not an instance that the constructor could ever produce. That's an integrity failure, and that's that we can't allow to happen. And then there's this nasty interaction with the Java memory model, which is, we've kind of gotten used to the idea that if you construct an object, others will see it in the state it was constructed in. Seems pretty reasonable, right? But once you start trying to flatten objects out, the memory model means that I can't necessarily atomically update it at once, and I might see an object not conform to its invariance. And that would be terrible, right? So this is an impediment to flattening as well. So it's a complicated design space. So let's go through those in a little more detail. So we've always known that object identity was flattening enemy number one. So the basic model is every object gets a unique identity, which is assigned when you say new foo. And what does the equals operator do? The equals operator says, are these two things the same object? And it does that by comparing their identity. And identity enables a bunch of things: mutability, layout polymorphism, locking, etc. And some classes really like that, and some classes don't need that. And unfortunately, the classes that don't need it are still paying for it. And in fact, having identity is a source of bugs. Like, we've all experienced the issue where two integer objects might be equal to each other if they're represent small integers, because those are cached, but might not be equal to each other if they represent large integers. And the first time you see this, you say, what the hell is that, right? It's very confusing when you see that the first time. So the reason object identity is an impediment to flattening is it essentially requires that the object lives in one place. So unless we can prove that objects are not aliased, it basically forces that box and pointer layout, and therefore no heap flattening and very limited scalarization for identity objects. So if identity is the problem, let's let people give up identity if they don't need it. Sounds easy, right? So that's what a value class is. You declare a class as a value class, and you're saying, my class doesn't have identity. That has a few consequences. You can't do the things that identity is there to enable, like mutation, but a lot of classes are immutable, so that might be okay. Value classes similarly are non-extensible. But again, for a class like complex or optional or local date, that's probably okay. Now, the key thing here is that valueness is not a performance characteristic. It's a semantic statement that says these instances of this class don't have identity. Purely semantic, but that semantic claim of I don't need this degree of freedom is what unlocks the VM's ability to optimize it more effectively. And a lot of classes that we write, especially most of the small classes we write, are morally values already. Numerics, dates, tuples, cursors, all of these are meet the requirements to be value classes. And in the JDK, we will probably migrate a lot of these. So what does it mean to be a value class? Well, it has pretty much most of the things that classes have. Fields, methods, constructors, supertypes, implementing interfaces, type variables, etc. The differences are actually pretty small. So the class itself is final, the fields are final, and most importantly, when I compare two value objects with equals, I'm comparing their states. I'm comparing their fields, not their identity, because there is no identity. And then there's a few things you can't do. You can't lock on them. You can't take a weak reference to them. And there's some minor restrictions on what kind of superclasses value classes can have. But this is actually a much simpler view of value types than we had in Valhalla several years ago. So if you have a value class, its instances are objects, just like any other class. We call them value objects. They're referred to by object references, just like any other class. The only difference is we're more likely to be able to optimize away the physical form of the object reference. And the reason we can do that is the lack of identity means that these things are freely copyable. If I have two instances of a value class and their fields are the same, then it doesn't matter if I have one object or that's aliased or two separate objects. It doesn't matter if I shred it into its fields, pass the fields around, and then reconstruct it into an object later. I can do that with no loss of information, and then it's the VM's job to decide when it would be fruitful to do that. And the effect of that is most of the time, if you're working with one of these on the stack in a local variable, nothing ever gets allocated at all. If you're passing them between methods, the calling convention is highly optimized. We don't allocate an object, we just pass the fields and registers. And the effect of this, which is really cool, is you can write immutable objects and mutate them by replacing them, like cursors and accumulators, and get the safety of immutability and the speed of mutability. So I'll show a few examples. This one is an immutable accumulator. So I have a record that holds the total. It's kind of a strange looking class, right? Because it's meant to be an accumulator, but it's immutable. And it starts out at 0. And I have this method to add something to it. What does that method do? The plus method is it allocates a new immutable accumulator with the new value. Now, if I use that in the obvious way, I create an accumulator, I loop through some array of things, and I call the plus method to add the length of each string. In the end, no accumulators will be harmed in this in this example. We allocate nothing. What happens is the total gets hoisted into a register, and that call to acc.plus just turns into, add something to that register. So it bottoms out at the exact same hand-tuned machine code you would have written if you were writing in an assembly language, but you get all of the benefits of object orientation and immutability and all of that. It's really cool. The same thing happens in calling convention. So if I have, say, a record for point that has double fields for x and y, and I want to determine, I want to generate the point that represents point on the unit circle for a given angle. And so what does it do? It calls cosine and sine and makes a point out of that. When I call that, you might think that a point gets allocated, but it doesn't. What happens is, even if it doesn't get inlined, it will basically just return the x and y in registers, and they can be used locally by the calling code. So the calling convention is highly optimized. Most of the time, nothing ever gets allocated. So we're doing this in phases. So there's a JEP for this, JEP 401, we're definitely dividing it into bite-sized chunks. So the first JEP delivers one new language feature, value classes. Just, that's the only syntactic change. It's the only conceptual change. And at the same time, we'll probably migrate a bunch of JDK classes like integer and optional and local date and such to be value classes. This is laying the groundwork, where it's laying the groundwork semantically by introducing the concept that not all objects have identity. And it's laying the groundwork for optimization, where we're able to deliver some optimizations like scalarization in local usage, optimized calling convention, some heap flattening for small objects. But at the same time, we're not throwing a pile of new complexity at people, and basically teaching people to ask the question, does this object need identity? If not, don't have identity because it'll just be in your way, and maybe you'll also get better performance. So the state of this is in really good shape. The spec has been stable for probably over a year at this point. We're just in the process of cranking through the implementation, but there's early access builds that you can download today. So that's part of the story, not the whole story. So what else is there? So nullability, somewhat surprisingly, turns out to have a relationship with flattening and density. So if I have a nullable reference to an identity-free complex, I need to include all the combinations of complex numbers plus one more distinguished value. And like I said, this is both a density hazard and a flatness hazard. And as I said, also it interacts with the memory model because as objects get bigger, that extra bit for null might actually push you over the threshold of the size of atomic operations on your hardware. Also, there's a reason primitives are not nullable, and it's not that we just don't want to pay the space for it. It's that nullability is not all that useful in the context of numeric code. Most numeric code, null would just be in the way. So again, just like with identity, if this is a degree of freedom that's not helping you, then you should be able to disavow it, and hopefully not only does your code get more clear, but it gets more optimizable. So okay, how do we do this? Well, there's an obvious answer. Let variables and types opt out of nullability. You've seen something similar in other languages. Scala, Kotlin, C#, Swift have all engaged some form of nullity control using the familiar bang and question mark operators. All of that was copied from another language. Nobody invented these things. But the nullability control that you may be familiar with from Scala or Kotlin is a vastly simplified version of the cardinality-based type system that was explored by the Microsoft C Omega experiment, which was really cool. But anyway, it's one of the most common requests that people make of, can Java have, can have null restriction? It might be one of those be careful what you ask for things, because it does bring in a fair amount of new complexity, but it is something that people seem to want, and it does synergize with Valhalla pretty well. We tried a few times in earlier iterations to make value types non-nullable by default, and that turned out to, not surprisingly, interfere with migration compatibility in a pretty serious way. So when you declare a value class, its instances are nullable unless you explicitly disavow nullability. Same with identity classes. So nullity control brings in some new challenges, like so if I have a field of type string bang, which means string but not null, well, what's the default value of that field? Well, during object initialization, the VM is going to write a null there. That's outside the value set of the type string bang. So it would be inconvenient if people were exposed to that null. And unfortunately, people are exposed to uninitialized fields during construction all the time. Because what's the first thing you do in a constructor? You call the superclass constructor. You haven't initialized your fields yet. So if you have a string bang field, and then your superclass constructor calls an overridable method from the constructor, it's going to see a null where it did not expect one. And that's unfortunate. So we've beefed up the definite assignment requirements that say you have to assign these things before you call the superclass constructor. Now, that's something we've never been able to do in Java, but we had another activity, JEP 482, called flexible constructor bodies, that allow you to put more stuff before the supercall. And one of the things that you can do there is initialize your fields. And in fact, if your fields are null restricted, you have to initialize your fields up there. You can't call the superclass constructor until you've done so. So that way, we don't allow invalid field values to be observed. We have a similar problem with arrays because you create a new array. It's even worse because arrays don't have constructors. You create a new array, and what does the VM do? It fills it with nulls, right? So we need a way to say, I'm creating an array of string bang, and here's the lambda to call to get the initial value of each element. Or here's a value to prefill on each element. You're not going to be able to say new string bang 10, nothing, because then you would be allowing an array of invalid values to escape. So there's some changes that have to happen to field initialization and array initialization. Now, the cool thing is we can do this incrementally. We can do null restriction completely separately from Valhalla, and we might. I'm not sure we will, but we certainly could. And there's a bunch of work there that can go on in parallel with the Valhalla work, like threading this through the type system, inference, bounds conformance, conversion, overriding, overload selection, pattern matching, blah, blah, blah. So there's plenty of work. We're able to do fairly comprehensive dynamic enforcement. So when someone tries to put a null where it doesn't belong, we can generate a null pointer exception likely earlier than if we allowed the write to proceed and then we used it at a later point. We engage the VM's help in detecting things like writing nulls into arrays and writing nulls into null-restricted fields. And then, like I said, the last bit we cover up with stronger definite assignment rules to make sure that these fields and array elements start out with a valid initial value. This is a complicated feature of the nullity control. It is going to be different from what you might be familiar with in Scala or Kotlin or Go or C# or Swift, because Java is different. And in particular, we care so much about compatibility and migration compatibility that the prime directive for the design of adding nullity control to the language is adding nullity information must be binary and source compatible. And that turns into some surprising consequences, but they're right, they're just surprising. Now, when we combine null-restricted types with value types, our initialization challenges that we just described are even worse, because if I have a variable of type string bang and I find a null in it, well, that's annoying, but it's not an integrity failure. It's just annoying. And I could probably point my finger at, oh, you wrote some bad code, it's your fault. But if it turns out that I have an object whose contents are invalid and I expose that to code who's expecting to see a valid object, that's an integrity failure. And we really don't want to allow that to happen. When we combine value types and null-restricted types, we need stronger enforcement, and we've engaged the VM's help to ensure that we have stronger enforcement to make sure that null-restricted fields are initialized before they can be observed. I mentioned the problem about local date, right? Like some value types like complex 0 is a great default. For local date, what's the default value for a local date if you don't give it anything else? January 1st, 1970, right? That's a terrible default. You know what else is a terrible default? January 2nd, 1970. In fact, all the dates are terrible defaults. And how many people here have interacted with some website who told you that your subscription expired in some neighborhood of January 1st, 1970, right? And how many people here got billed for interest and penalty on 50 years of that? Right? It's a terrible default. It's a bug waiting to happen. So some value classes have good defaults, some don't. That's going to become part of the programming model. So this is important because we want to flatten these things. If we want to flatten these things, that means we don't have the benefit of a pointer that guards access, and might be null before we can get to the object state. So we need to make sure that the object state is always in a good state before it can be observed. And one of the ways that we did that is to strengthen class initialization at the source level, but we also strengthened it at the VM level. And so the source stuff was already on the way coming from flexible constructor bodies, but we turned up the volume, not only adding new definite assignment checks, but adding JVM verification to make sure that all of the fields that must be strictly initialized are strictly initialized before you make the supercall. Fortunately, that has no runtime cost. It's all done at verification time. So there's this hidden concept that you won't see in the language description called strictly initialized fields, and it's it means a field that has to be initialized before the superclass call in the constructor. All fields of value types have to be strictly initialized. All null-restricted fields have to be strictly initialized. There might be some others that have to be strictly initialized as well. This, like I said, it doesn't show up in the language syntax. There's no keyword for strict, but it's a concept that you're going to be exposed to because the compiler will say, this field needs to be initialized earlier. Go do it. And that's because we want to make sure that field is initialized before it can be observed. This was a really good example of a sort of hidden enabler where strictly initialized fields was not on anybody's bingo card for Project Valhalla. No one is knocking on the door saying, give us strictly initialized fields. It turns out, surprisingly, that several of the really hard problems that we've been bashing our heads against for the last 10 years just went away when we added this. It's kind of surprising. So this is an old sloppiness in the language about exposing objects before they're fully initialized that had been a source of problems. We didn't even realize it until it was pointed out to us. So some quick performance numbers to give you an idea of what the best case looks like. If you're working with arrays of values like matrix computation, things like that, we see dramatic speedups on these kind of operations. These come from a couple sources: scalarization, better locality, reduced allocation. All of those things come together. But large matrix multiplication, we saw 6x throughput improvement. Summing up arrays of structures, depending on the configuration, 3x, 8x, 12x, improvement, mostly because of increased locality. So, these optimizations are pretty powerful. If you don't need identity, you should think about giving it up because you may be rewarded. Now, like I said, the Java memory model has like some unfortunate news for us. If you remember back in the old days of Java, longs and doubles, it was possible for them to tear under race, so that if one thread is writing it, another thread is reading it, and you're not properly coordinating, you might see the low 32 bits of one write and the high 32 bits of another write. And that was because back then, most machines didn't have cheap 64-bit atomics, and we wanted long arithmetic to be fast, and code with data races is broken anyway. And so, like, it seems a very un-Java thing to tolerate, doesn't it, right? It's like, oh, sometimes your numbers are garbage, sorry. But the alternative was also pretty bad. Numerics had to be fast. Concurrent numeric code was not that common. The problem only showed up in programs that had serious failures already. And then we had this like fig leaf we could cover ourselves with. Well, technically, it is returning a valid long, so it's not violating type safety. I don't want to get behind that argument, but sometimes you retreat to some weak arguments in order to get on with the day. But so like then hardware got better, this problem went away, we all sighed a big sigh of relief, and now here come the 128-bit numerics. And same story all over again, right? So, if we want to choose to flatten larger values, we're going to confront this problem, right? Because we still have the risk of tearing, and some things like complex, double complex, we might be willing to make the same compromise we made with longs, and that might be okay because we'd rather have the flattening than the protection against data races. On the other hand, some classes like let's say a long range has an invariant, and it would be really bad to like read a long range and find out that the lower end was bigger than the higher end, because that violates one of the invariants of the classes. And so whether or not we allow these things to be flattened is a complex trade-off that we have to put in the hands of the class authors, because it's a trade-off of performance for integrity, and it involves a lot of domain-specific trade-offs. So for things that are more like a long, like big integers or complexes, those are good candidates for allowing tearing. For classes like range that have invariants, they're not candidates for tearing. And there isn't a one-size-fits-all answer. So we're starting with the safe default, and we will let you opt out if you need to. A lot of these restrictions, especially the tearing restrictions, don't apply if something is final all the way up, because you're not going to have racing rights. So we don't have to be quite as quite as careful, which is another good example of if you don't need mutation, disavow it. You may be rewarded with better performance. So how are we doing? So in all cases, value objects are going to get excellent on stack and calling convention optimization. Regardless of size. Well, okay, if you have a value object that's a million bytes long, we don't have that many registers. We're probably going to box it into an object and pass the reference. But that's something that the VM is going to worry about for you. Nullable value types of less than 64 bits will be routinely flattened in the heap. Non-nullable value types of 64 bits can also be flattened, and larger values can be flattened if they're immutable all the way up, if you opt into relaxed atomicity, and when the hardware gets better, and it is getting better, so like AMD chips already have efficient atomic 128-bit operations. They do have to be 128-bit aligned, so there's a trade-off of density for flatness there. But as the hardware gets better, the threshold of flattening will go up. So 64 bits is not a magic number. It just happens to be where the consensus hardware is these days. So, as a good reminder, this was a real success story, that sort of brought us back, to our roots, because the Java philosophy is that flattening should always be an optimization. Sorry, optimizations should always be in the purview of the VM. We don't want users trying to pre-optimize their code, because the VM is going to do a better job. And so flattening certainly fits into that model. It should be a pure VM optimization. The language model should be about program semantics. We should enable you to express suppress the semantics that you need, that disavow the degrees of freedom you don't need, and the VM should optimize it for you. And the history of the alternative is terrible, right? So how many people here remember the register keyword in C? Right, this was a disaster because very quickly after its introduction, compilers got so good that they just started ignoring, the register keyword because the compiler did a better job of register allocation than humans could. So we're certainly not going to have a flat keyword, in the Java language. So the real challenge was, what are the right set of semantic levers that make sense to the user, but also enable the optimizations that we want to enable? And along the way, we found plenty of wrong levers, and we leaned on them and didn't like the results. So fundamentally, we went back to our roots and say, give users the opportunity to opt out of degrees of freedom they don't need, which is both semantically useful and potentially enables better performance. And then along the way, like I said, we had to fix some holes in the initialization protocol. As a result, when we did that, our migration compatibility story got better as well. It would have been awful to add value classes and not be able to migrate integer or optional. It would be awful to add non-nullable types but not be able to refine existing libraries to use them. And the earlier iterations had some real gaps in migration compatibility, which we have a much better story for now. Of course, like the ultimate migration compatibility problem is serialization. I can't get through a talk without talking about this. So we paid the serialization tax in this feature too. We probably spent 10 or 15% of our brain cycles dealing with what about serialization, and there was a lot of heroic rewriting of the serialization stack required in order to be able to support value classes. Because the way that serialization works is it creates an empty object and pokes values into it. Well, value fields are immutable. The VM's going to enforce that they're immutable. And so serialization is not able to work in the old way. So the good news is we made legacy serialization work, but value types are a perfect fit for the marshalling work that Victor and I talked about yesterday. So that is actually a much better story. So, okay, I see like some people have already left the room saying, this is boring. I didn't hear anything I didn't know already. It's very natural at this point in the talk to say, wait a second, you've been working on this for 10 years and that's it? That's the whole thing? Value classes and bangs? And, well, mostly, yeah. But it's like the old Pascal quote. I apologize for writing you a long letter. I didn't have time to write a short one. It took a long time for the obvious thing to emerge and the things that we needed to do in order to make it possible, like strict initialization. So in the end, if you don't need identity, opt out with value classes. If you don't need nullability, opt out with null restriction. And most of the rest of the complexity disappeared. So, like I said, this took a long time to get to the point where the intrusion into the VM, the language, and the user model was this small. It was a gradual process, but like I said, we navigated to the virtuous collapse. Also, kind of as a bonus, as we were watching this virtuous collapse happen before our eyes, there were a lot of features that were on our wish list of, boy, it'd be really nice if we can make this happen, but oh no, that'll never happen. We just have to give up on that. All of a sudden, the things that we gave up on were not problems at all. Right? So finding the right model not only makes things simpler, but it makes them richer and more powerful. So if you've been following the discussions over the last 10 years, all of these things that I list were hot discussion items of why can't you do this? And our answer was like, yeah, it really sucks. I wish we could do it, but we just don't see a way to do it. And then all of a sudden we did. So all of the intrusion into the VM surface, new bytecodes, new constant pool forms, new type descriptors, all gone. Just a few new bits in the class and a new attribute for null enforcement and some new verifier rules. So, like I said, what took you 10 years? Obviously, there was a lot of work, but there was also finding the right way to frame the problem, finding the right user model, burning our way through the initial obvious but wrong ideas, and figuring out what the right balance of what do we ask the VM to do versus what should the language do. And our initial guesses on some of those were wrong, and we had to adjust. But just in case you think we've just been sitting around for 10 years, I asked the team to make a list of the significant investigations we went through and abandoned. And this wasn't even all of it. This was just I didn't want to spend hours and hours on it. This was one or two people went through their mail archive and looked for significant discussion threads. And, there's a lot of work that went in that, is either just informed what the correct model is or just turned out to be ideas we didn't need. Okay, so there's four. If you've been keeping track, you've seen I've alluded to 3 JEPs so far: value classes, null-restricted types, null-restricted value types. There's more work to do. So one of the sort of mop-ups after that is dealing with the gratuitous divergence between int and integer bang. They should be identical after Valhalla is done, but they're not quite identical. And we can close 95% of those gaps. So right now you can't use primitives as receivers. You have to cast them to a box type instead. They don't participate in covariant overrides or array covariance or type arguments. We can fix all that. There's a JEP for that. And that's sort of a filing down rough edges and mopping up. There's still a few that we can't get rid of for compatibility reasons, most notably the complicated rules for overload selection. But we can make primitives look much, much, much more like their null-restricted box counterpart. So are we done then? Hell no, right? Okay, how long do you think it's going to take when we say, great, good news, we have 16-bit floats and complex numbers now, before people say, excuse me, where's my operator overloading, right? So it will not be long. Yes, we know. Of course we know. Now, operator overloading has been the third rail for a lot of languages. There have been many disasters hatched in the area of operator overloading, so we understand the risks. We're working on something. I don't want to spend a lot of time talking about it because that's way in the future, and we have problems to solve in the present, but we think we have a pretty reasonable story here. And there's also a follow-on work about pushing specialization through the generic type system so that when you have an array list of int, you actually get it backed by an int array and not an object array. And this has been a design activity that's been on a slow burn for quite a few years. There's a beautiful design document that John wrote. We call it a rough draft. You'll look at it and say, oh my God, this looks like a finished specification. It's still a rough draft. It's a complicated space, but it's a tremendous first step. So just summing up, big progress in the last 2 years is exposing a sane programming model that unlocks the optimizations that we want, that unlocks the migration compatibility that we want, and surprisingly, the language and VM changes are shockingly small. The implementation complexity, not shockingly small. So it's going to take a while. We've got 4 JEPs, in the pipeline, and there will be more to follow. Of course, JEP 401 is well on its way. I'm not going to make a prediction about a number because I don't do that. But the spec for JEP 401 has been stable for like a year, and the implementation has been proceeding quite nicely. So with that, I managed to make it with 2 minutes to spare. I don't know how I did that. So we can take a few questions, and then later this afternoon we have an Ask the Architect panel. So if people have questions that we don't get to, we can take them then. So question here, the third row there. So unions of value types? Yeah, so the question is, will we get union types in the Java type system, please? We have enough other complexity to wrangle before we go diving down type system rabbit holes. So maybe, but this is not something that moves us towards that. Sir, here.
I'm curious about the immutability part.
Yep.
There are classes like strings, for example, in which hashcode computation is very key for the performance of hashcode. And it's kind of stored, like giving up on the immutability part.
Yeah.
If we give up on immutability completely, we can make use of caching of hashcode.
Yeah, so the question is, what about string? String is immutable, right? Wrong. String is immutable because it caches a mutable hash code. So the obvious way to do it, you're right, we would not be able to migrate string to be a value type. But there are tricks. A string is backed by an array, which is always immutable. We could use the low words of the array to store immutable hash code, and then the state of the string would just be an array reference. It would get flattened away. So we could do that. We're not doing that right now, but there is a possible path to being able to launder mutability behind an immutable pointer. And when the time comes, we will avail ourselves of crazy tricks like that. We might not do it for string because it changes the behavior of interning, and there is a lot of code that may be dependent on, it's been this way for 30 years, and I've built my whole tower based on this assumption, and people might not like the trade-offs that come with it, but that's another discussion. Okay, I think we have time for one or two more over here and then over there. Yeah, so the question is, all right, so the Kotlin guys love their null restriction. Are they going to be happy about what we're doing? I don't know. I don't know how to make people happy. But what we're doing is different from what they're doing. They're certainly going to tell us it's different. Some of them will tell us different is bad. That happens. That's what people do. I think for the most part, it will be a good thing because there will be more information in the API interface that could be mapped through to other languages where it could be interpreted. So I think overall it will be a plus, but stay tuned for plenty of complaining about you did it differently, we had the right answer, you're a bunch of idiots. So I want to take his question because we're almost out of time. So the question is, are there more code examples, or are they all trivial things like this? So we have quite a lot of code examples in our base of performance tests. So like our performance team has probably written more Valhalla code than like everybody else in the world put together, which is like how you want it at this stage of the project. But I think the real question you're asking is, where's the effective Java chapter for how to use value classes effectively? And yes, we're aware. All right. Thank you very much, everybody. Take care.